So, in the last class we looked at a single normal operator and looked at how the spectral theorem looks like in both the forms, right. One was the integral with respect to the projection valued measure, second was realizing the normal operator as multiplication by z or multiplication by lambda on the spectrum with respect to some measure, right. So, in the cyclic case of course, it becomes a very nice operator multiplication by lambda with respect to a probability measure and so on. In the general case you have to take a direct sum and so on, but then there are ways of putting it together and thinking of it as multiplication by lambda with respect to some measure. Okay, and then we so let us let's look at the exercise once more. So, if I take a normal operator, so Tf equal to phi times f, right, on L2 of mu. So, this essentially gives you all normal operators, right, by spectral theorem. If you define the new measure nu like this, then I can realize my operator T, which is given by multiplication by phi as multiplication by z on L2 of nu, right. All right. So, maybe one more exercise. So, let us say this is one. Second one, once you have this spectral theorem, things are you can use the multiplicative the spectral theorem in the form of multiplication of functions to deduce various things. Okay. So, let T be a normal operator on a Hilbert space and so on. Then T equal to T star. So, T equal to T star meaning it is self adjoint if and only if the spectrum of T is contained in the real line, right. So, remember we are starting with the normal operator, we are saying it is self adjoint if and only if the spectrum is contained in the real line, right. And similarly also T is unitary. So, again remember that we are starting with the normal operator, T is unitary if and only if the spectrum of T is contained in the unit circle equal to 1. Okay. Well, how does it follow? It follows immediately from the way we have written down the spectral theorem in terms of multiplication operators, right. So, let me see, let us see how this follows immediately. I will leave the details to you. I can write down T as multiplication by some bounded function phi, right. This is the spectral theorem. In fact, if you choose the measure etc. appropriately, it is actually multiplication by z on the spectrum, right, with respect to some measure, right. But we do not need for deducing this, we do not need that much of information. Now, what is m phi star? So, T is unitarily equivalent to multiplication by phi, right. So, T star is unitarily equivalent to multiplication by phi and its adjoint, right. Its adjoint is simply multiplication by phi bar, right. But if T equal to T star, then that is that meaning it is self adjoint, that will mean that m phi equal to m phi bar, but then phi will have to be equal to phi bar, right. So, T self adjoint implies m phi star equal to m phi implies phi bar equal to phi, right. Implies phi is real valued, which means its essential range is going to be contained in the spectrum. So, all this is if and only if. Okay. So, T is self adjoint if and only if, and this is if and only if, right. So, everything follows immediately from realizing the normal operator as a multiplication operator. So, this is one of the advantages. Okay. So, looking at the projection valued measure and the integral, this may not follow immediately. Similarly, for the unitary, right. So, if T is unitary meaning T star equal to identity equal to T star T, right. But T star is m phi star times m phi, right, but then that is m phi bar times m phi, and so it is m mod phi square, multiplication by mod phi square should be identity. So, mod phi square should be 1, right, which is same as saying phi bar. So, phi should have modulus 1, right. So, otherwise this will not happen. That is same as saying the spectrum or the range of phi is contained in the unit circle, which is same as the spectrum is contained in the unit circle. All this, if you look at the finite dimensional case, this will be very clear, right. If I have a diagonal operator, when is its diagonal matrix, when is it self adjoint, the eigenvalues are real. If and only if the eigenvalues are real, which is same as saying the spectrum is in the real line. Similarly, it is unitary if and only if the eigenvalues are have modulus 1. Right. Remember, we are starting with the normal operator. So, it is diagonalizable, the diagonal entries have modulus 1, then it is unitary, right, which is same as saying the eigenvalues are contained in the unit circle. All these are simply generalizations of whatever you already know in the finite dimensional case, which is obtained after knowing the spectral theorem, right. That is precisely what we have done here. Okay. So, now we will restrict ourselves to self adjoint operator. Okay. So, we will look at the self adjoint case. Self adjoint case in more detail. Okay. Now, as I said, one can do this for normal operators as well, but we will stick to the self adjoint case where, because some of the things get simplified, because the spectrum is going to be contained in the real line and there is a way. So, what we are going to do is to sort of develop the projection valued measures for the self adjoint case, except that we do not call them projection valued measure. I will explain that. This would be called a resolution of identity, which we can define in the case of normal operators as well, but we will stick to the self adjoint case. Okay. So, let me start with the definition and then I will try to motivate this. So, definition. So, we may not well, if there is time we will prove something, but we may not use this resolution of identity today, but it will be used in the next class onwards. So, let H be a Hilbert space, H be a Hilbert space. A resolution of identity, is a function t going to E sub t. Okay. So, where is t? T is going from, t is in the real line. So, these are all in the real line. E sub t's are going to be projection. So, this is like the projection valued measure, except that this is a function, right. It is taking the points on the real line, that is t, to projections. In the projection valued measure we had sets going to projections. Okay. So, we will come to that soon. So, t going to E t from the real line to the space of orthogonal projections, okay, on the Hilbert space H, on H, such that so three properties. So, this is like, if you have seen probability, this is like the cumulative distribution function of a probability measure. So, let me write down all this. T less than S implies E sub t. So, E sub t is a projection less than or equal to E sub S. Okay. What does it mean, less than or equal to E sub S? So, let me define that. We probably used it earlier. So, definition, if A and B are self adjoint operators, bounded operators, then A less than or equal to B implies or means B minus A is a positive operator, What is a positive operator? So, B minus A is self adjoint, right, because A and B are self adjoint and B is bigger than A, right. That means B minus A is positive. So, just like what you see in the real line, x is greater than y, meaning x minus y is a positive number, right. So, B minus A is a positive number, meaning B minus A acting on a vector x, inner product with x is positive, right, or in other words Bx x is greater than or equal to Ax x, right, for every x in the Hilbert space, right. Then you say B is greater than or equal to A. Okay. So, remember that these are all self adjoint to start with. Okay. Now, we are looking at a resolution of identity and t going to E t, these are all taking values in the space of orthogonal projections, right. So, when I say orthogonal projection, each E t has the property that E t star equal to E t square equal to E t, right. So, they are all self adjoint, and so E t less than or equal to E s means that E s minus E t is a positive operator, right. So, that is E sub s minus E t is a positive operator. Of course, it could also be 0, but that is included. So, this property is of course called monotonicity, right. As s becomes bigger, you have a bigger operator in some sense, right. 2 limit of t going to minus infinity of E t equal to 0 and limit t going to plus infinity of E sub t equal to identity, but in the strong operator topology, right. These are projections. So, E sub t are projections and I am taking the limit of t going to minus infinity, I should get 0. When I go to infinity, I should get the identity operator, but these convergences are in the strong operator topology, where the convergence is in the strong operator topology, right. So, this is very similar to what you have seen in the in the projection valued measure, where the convergence was in the strong operator topology, right. The countable additivity part was in the strong operator topology. I will come to this second property again, but let me write down the third one and then explain this. Limit t decreasing to s, right. So, this is the right limit, t is going to s from the right side, E sub t equal to E sub s, okay, again in the strong operator topology. In the strong operator topology. Okay. So, what are these properties? So, let us look at that. The third one is simply right continuity, right. So, right continuous. What is the second one? So, this is like the property of a probability cumulative distribution function of a probability. Okay. So, like the CDF. So, if you do not know what it is, it is okay. I will explain a little bit of this soon. So, like CDF cumulative distribution function, or sometimes it is simply called distribution function of a probability measure. Right. So, when we define projection valued measure, we saw that it was like a probability measure, and this is precisely well, more or less the same, except that we are writing the cumulative distribution function instead of the probability distribution function. Okay. So, let me take 2 minutes to define or explain the similarity between cumulative distribution function. Okay. So, compare or comparison with cumulative or distribution function. Okay. So, distribution function of a probability measure. So, earlier remember it was projection valued measure, here also these things are projection valued, okay, but instead of having a projection valued measure, we have something very similar to the cumulative distribution function. So, if so let us say P, okay. So, if P is a probability measure on the real line. So, let us say Borel probability measure on the real line, then if I define f of x to be the probability of minus infinity to x, let us say closed, that interval that has all these three properties. Okay. So, what are the properties? Now, everything is real value, right, positive, actually positive because probability, and so it is valued between 0 and 1, right, not projections, but these three properties monotonicity. So, if I take t less than s, f of t will be less than f of s, right. So, that is the first thing. So, you see that if, so let us look at the three properties. One, if t is less than s, then f of t is less than or equal to f of s, right, because t is less than s. So, I am looking at probability of minus infinity to t and minus infinity to s, and minus infinity to t is contained in minus infinity to s. So, that is the monotonicity property of the measure, right. So, 2 limit t going to minus infinity, I will have e sub t equal to 0, and similarly the other one is identity, right. In this case, because these are all scalar valued. So, limit t going to minus infinity of f of t, this is 0, right, because minus infinity, the set minus infinity to t, as t goes to minus infinity goes to the empty set, right. So, it is 0, and that is one of the continuity theorems for measures, right. And similarly, if I look at limit t going to plus infinity of f of t, well, that would be probability of the whole space real line, which is 1, right. So, instead of the identity operator, I will get 1, the number 1 there, right, because we are looking at the cumulative distribution function. Third, the right continuity, right, these are right continuous functions. Okay. So, f is right continuous. Again, right continuity follows from the fact that if x n decreases to x, so x n decreasing to x, the sets will decrease to minus infinity to x, right. So, it follows that again due to the continuity for the measures, you have this this property. So, think of E sub t as a cumulative distribution function associated to a projection valued measure. If I take a function, so just to complete the measure theoretic part, if f is from the real line to let us say 0 1 with 1 2 and 3 properties, right, these properties, one can define a probability measure, let us say p, or I will say mu a b to be equal to f b minus f a, right. If f is differentiable, you can actually write it as an integral and all that, that derivative will be the probability distribution function of mu. Okay. Well, this defines it only on these sets A B, right, A open and B closed, but then you can take finite disjoint unions of that will give me a field, and you prove that this is actually a countably additive measure there. Then the Carroll-Theodori extension theorem will help you to extend this to the sigma algebra, which is the Borel sigma algebra. Okay. So, that is one way of generating the measures. So, if I have a right continuous function with these properties 1 and 2, then I have actually a probability measure, and this function f is called the cumulative distribution function. So, you should think of the resolution of identity to be the cumulative distribution function for a projection valued measure. How will you generate the projection valued measure? Of course, just like what we have defined the mu here, you can define the projection valued measure p also, right, for sets of the form A B, where A is open at A and B closed at B, by simply taking the difference, right. You look at E sub B minus E sub A, that will give you a projection. Of course, you have to prove that it is a projection, we will see that immediately. And then of course, you have to you have to extend it to other measurable sets, right. This will define it only for intervals of certain kind and finite disjoint union, and then you have to extend it to other sets. Okay. So, we will not do that, we will just stick to the cumulative distribution function, which is the resolution of identity in this case, and then try to define the integrals exactly like you will do it in measure theory. Okay. So, let us continue. So, just to complete the definition, if so let E t, so t belonging to R be a resolution of identity, So, remember that all each E sub t they are all projections, right, with all those property monotonicity and right continuity, and at minus infinity it is 0, at infinity it is 1, right. Be a resolution of identity if there exist A and B, right, finite A and B such that E A minus epsilon equal to 0 and E B plus epsilon equal to 0 for every epsilon positive, then we say that E is supported in AB, right. So, in the real line I have this interval AB, and for any point here the projection is 0, for any point here the projection is 1, right. So, remember it is increasing, right, as you go from left to right it increases. So, at up to A it is 0, then it slowly increases, and once you reach B it becomes 1, right. So, it is something like this, right, and then it stays as 1. So, 1 meaning the identity operator. Then we say it is supported here, because the probability measure if you look at it is going to be supported in this set, right. If the cumulative distribution function is like this, when I subtract, right, I am going to look at f b minus f a quantities, you will see that it is supported in A b. Okay. So, let me write down a lemma, and maybe we will have the time, we will probably have the time to prove it. So, at least let me write down the lemma. Let P Q be two self-adjoint projections, orthogonal projections. So, projections meaning, so this means that P equal to P star equal to P square, and similarly Q equal to Q star equal to Q square, right. That is what we mean, projections on a Hilbert space, okay, H with P less than or equal to Q. Okay. Then we have the following assertions. So, first one, range of P is contained in range of Q. Okay. So, range of P will be contained in range of Q if P is less than or equal to Q. Q minus P. So, whatever is remaining. So, I mean keep in mind that we are going to apply this to E sub t, right. So, E sub t and E sub s. E sub t is less than or equal to E sub s if t is less than or equal to s, right. And so, all these things will be applicable to the resolution of identity which we are looking at, that is why we are proving this. So, Q minus P is a projection. So, when I look at E t minus E s, that is also going to be a projection onto range Q intersected with range P and its orthogonal complement. Okay. See Q P equal to P Q, okay, that is sort of trivial. Okay. So, let me repeat, if I have two self-adjoint projections with this property that P is less than or equal to Q, then range of P is contained in range of Q, Q minus P, that is what is remaining in Q, right. If you throw out P, Well, it is a projection to what is remaining in the range of Q. So, if you look at this thing, so let us see what this is. So, let us say this is range of Q, this is range of Q, okay. Range of P is contained in range of Q, right. So, there is something here which is range of P, okay. Now, if I, so in the whole Hilbert space, if I look at range of P orthogonal complement, then it will have something in range of Q and whatever is outside, right. So, range of P orthogonal complement is whatever is outside range of P, which is orthogonal to it, of course. So, if I intersect with range of Q, that is simply what is looking at what is the orthogonal complement of range of P inside range of Q, right. So, essentially range of Q can be written as range P direct sum range P complement intersected with range Q, right. So, range Q you split into two parts, one is orthogonal complement of one is range P, which I know that is contained in range Q from the first assertion, and whatever is in the orthogonal complement of range P, but inside range Q, right. So, range Q is split into two parts, range P and its orthogonal complement in range Q, and Q minus P is a projection to that remaining part, that is what we are saying, and QP equal to PQ, that is a trivial thing. So, let us prove at least the first assertion and we will complete it in the next class. Okay. So, proof A, if x belongs to range P, then P x equal to x, right. So, on the range of P, P acts like identity, right. So, P x equal to x and P x inner product with x equal to, of course, x inner product with x, because P x equal to x. Okay. So, if P is less than or equal to Q and x is in the range of P and x is in the range of P. So, there are two conditions, P is less than or equal to Q and x is in the range of P, then x inner product with x equal to, because x is in the range of P, I know that this is P x inner product with x, but P is less than or equal to Q. So, this is less than or equal to Q x inner product with x, which is of course less than or equal to x inner product with x, because Q is a projection, right. True because Q is a projection, right. For any projection this is true. So, I started with x inner product with x and I know that it is less than or equal to this. So, this would imply that Q x inner product with x equal to x inner product with x, and that implies that x is in the range of Q. Okay. So, this implies x is in the range of Q. Okay. So, this part well, this is actually pretty trivial, I will leave it as an exercise. Okay. Again, you can use the orthogonal complement argument to show that if Q x inner product with x is equal to x inner product with x, that means no part of x is sort of thrown away by Q, right, that is what it means, otherwise it will be strictly like this and x inner product with x. Okay. So, maybe we can prove the second one as well. So, B range Q, so we will stop with this. So, range Q equal to range P direct sum range P orthogonal complement intersected with range Q, right. So, that is how you write the orthogonal complement, right, whatever is orthogonal to range P inside range Q, right, that is the second term here. Now, I want to show that Q minus P is the orthogonal projection to the orthogonal complement of range P inside range Q, right. So, if x belongs to range Q, then well x equal to q x equal to, I can write this as, well I write this as p x plus q minus p x. Okay. So, where is p x? P x is in the range of p, right. So, q minus p x is the remaining part, right, and check that So, I will this is a more or less straightforward computation. Check that q minus p is a projection, well, you can use the A part. Okay. So, use the first part, and p q equal to p, okay. Because q is less than or equal to, I mean range of p is contained in range of q, right. So, because of that p q equal to p, okay. So, the C q p equal to p plus q minus p into p equal to p square equal to p equal to p q. Okay, q minus p into p is 0, right. So, q minus p into p equal to 0, because range of q minus p and range of p are orthogonal to each other, right. So, range of q minus p is this orthogonal combination, this is a direct orthogonal direct sum, right. Okay. So, we will stop here. What we did was we defined resolution of identity, but we have not proved any properties of that yet. Okay. So, we have this E sub t's, which is the resolution of identity, which is like the cumulative distribution function of a probability measure, and well, we just proved a lemma for projections, and the projections you will see, because p, the condition was that p less than or equal to q, and that comes from E t less than or equal to E sub s if t is less than or equal to s, and we can use that. So, you will see that E s minus E t, they are all projections, okay. And whenever these intervals are distinct or disjoint, so let us say I have t 1 s 1 and t 2 s 2, right, and these two intervals are different, then E s 1 minus E t 1 and E s 2 minus E t 2, these are going to be orthogonal projections, that you have already seen in the definition of the projection valued measure, right. If I have two disjoint sets E and F, then P E times P F will be 0, right, which is same as saying the range of these projections are orthogonal to each other. This we will see immediately from this lemma, at least for disjoint intervals, okay. But and then we will see how to develop integration with respect to this resolution of identity. Okay. So, we will stop here for the time being.